Assalamualaikum and good day, sir. My name is Wana Zifa Azul binti Wan Azman. My metric number is 288197. Today, I will explain the implicit function that was related to this assignment. An implicit function is a mathematical function where the dependent variable is not expressed explicitly in terms of independent variables. Instead, the relationship between the variables is described through an equation or a system of equations. In other words, the dependent variable is defined implicitly by the equation rather than being expressed as a direct function of the independent variable. Implicit functions can arise in various mathematical contexts, such as algebraic equations, differential equations, and implicit curve or surface. They are often used when it is not possible or convenient to express the dependent variable explicitly in terms of the independent variable, or where the relationship between the variables is more naturally expressed through an equation. Implicit functions also have three different cases, which is the single equation case with a single independent variable, next, the single equation case with several independent variables, and lastly, the simultaneous equation case with two independent variables. Next, I will talk about the Jacobian metric function, also known as the derivative matrix or the Jacobian metric. It's a mathematical construct used in calculus and vector calculus to represent the partial derivative of a vector value function with respect to its input variables. It plays a crucial role in multivariable calculus, optimization, and differential geometry. The Jacobian metric can be used in various applications, including calculating gradients. The transpose of the Jacobian metric can be used to calculate the gradient of f, which provides the direction of steepest ascent in multivariable optimization problems. Secondly, change of variables. When performing a change of variables in multiple integration or coordinate transformations, the Jacobian metric helps account for the stretching and rotation of the coordinate system. Next, linearization. The Jacobian metric allows linear approximations of the function near a point. The first-order Taylor expansion of f can be expressed using the Jacobian matrix. Overall, the Jacobian metric function provides a way to analyze and understand the relationship between variables in vector value functions, enabling the study of complex systems and the development of mathematical models.
Okay, now we go into questions A. Show that the two conditions of the implicit function theorem are satisfied at the equilibrium point. So for the first condition, the function f1, f2, and f3 have continuous partial derivative with respect to all exogenous variable, which is y, c, and t at the equilibrium point. So thus the first condition are satisfied. For the second condition, we will use the Jacobian functions to prove they are satisfied. If the Jacobian determinant are not equal to 0, so means they are satisfied. So for this question, they are given three equations. The first is f1 of y, c, t, I0, g0 is equal to y minus c minus I minus g equal to 0. For the f2 is equal to c minus c of yd equal to 0. F3 is equal to t minus t of y equal to 0. So we will transform these three equations into Jacobian metric form. Okay, in the metric form, for the first row, delta f1 divided by delta y, delta f1 divided by delta c, delta f1 divided by delta t. For the second row, delta f2 divided by delta y, delta f2 divided by delta c, delta f2 divided by delta t. For the last row, delta f3 divided by delta y, delta f3 divided by delta c, delta f3 divided by delta t. Okay, there is the function. So the answer for delta f1 divided by delta y is equal to 1. Delta f1 divided by delta c is -1. Delta f1 divided by delta t is 0. Delta f2 divided by delta y is equal to negative c price of yd. Delta f2 divided by delta c is equal to 1. Delta f2 divided by delta t is equal to c price of yd. Delta f3 divided by delta y is equal to negative t price of y. Delta f3 divided by delta c is equal to 0. Delta f3 divided by delta t is equal to 1. After that, we want to evaluate this metric. What we are going to do is take the first term, the partial derivative of f1 with respect to the y, and we multiply it by 2 by 2 matrix, which is outside of its row and column. So means that the derivative of f1 with respect to y ignore everything that in its row and column. So the answer is 1 multiplied by 1 times 1 minus 0 times c price of yd plus 1 multiplied by negative c price of yd times 1 minus c price of yd times negative t price of y plus 0 multiplied by negative c price of yd times 0 minus 1 times negative t price of y. And the answer is 1 minus c price of yd minus c price of yd times negative t price of y. And in the end, the answer is negative, so they are not 0. Therefore, the second condition is satisfied because Jacobian determinants is unequal to 0 and not singular.
Now let us move to question B, which is ask us to, using the implicit function rule, derive the expression and show the algebraic sign for each partial derivative. To totally differentiate the equation f1 y star c star t star I g is equal to y star minus c star minus I minus g is equal to 0, f2 y star c star t star I g is equal to c star minus c yd is equal to 0, and f3 y star c star t star I g is equal to t star minus ty is equal to 0. We need to derivative each term with respect to the variables y star, t star, and g. Same the method to the second equation for f2 years and third equation f3 years. So now we need to collect terms and divide each terms by partial of y with respect to g. We will derivative each equation with respect to g. So let us move to the equation 1, f1. Now we can divide each term by g, and please note that dividing each term by partial of y with respect to g is assumed that the partial of y with respect to g is non-zero. If the partial of y with respect to g is 0, this means the division would not be valid. To convert the equation, f1 y star c star t star I g is equal to y star minus c star minus I minus g is equal to 0, f2 y star c star t star I g is equal to c star minus c yd is equal to 0, and f3 y star c star t star I g is equal to t star minus ty is equal to 0. We need to converting them into the matrix form, so we can rewrite them as a system of equation. So let us define the variables and constant in the following. Okay, where A is the coefficient matrix, X is the variable sector, and 0 is the 0 vector. On the right hand side, we can see the total differential equation that is in metric forms. For example, equation f1, the answer is 1 since the differentiating f1 with respect to y star gives 1. Here we also got the partial of f1 over partial of c star is equal to negative 1 since derivative f1 with respect to c star gives negative 1. And we also got the partial of f1 over partial of t star is equal to 0 since t star doesn't appear in f1. And the derivative of negative f1 with respect to g is given 1. For equation f2, we differentiating f2 with respect to y star, we obtain negative cyd. Next, we derivative f2 with respect to c star, we obtain 1. Derivative f2 with respect to t star, we obtain cyd. The differentiating of negative f2 with respect to g, we obtain 0. For equation of f3, we differentiating f3 with respect to y star, we obtain negative ty. And we differentiating f3 with respect to c star gives 0. Differentiating f3 with respect to t star is given by 1. So the differentiating of negative f3 with respect to g is given 0. To apply the Kerman rules, we need to find the determinant of the Jacobian matrix J. We can refer to the question A for the determinant of Jacobian matrix. Next, we are going to replace each column of Jacobian matrix with the column vector on the right-hand side of the equation. So to contribute the determination, remember we just take the top left entry multiplies it by the bottom right entries and we put a minus in the between. And we take the bottom left entry and multiply that the top right entry. So we get 1 plus 0 plus 0 is equal to 1. So to find the partial of y with respect to g, we need to use determination of j1 over determination of j, which is equal to 1 over 1 minus cyd plus cyd times ty, which is become positive. The result, the answer we obtain y star and g is a positive relationship. This means that when the government expenditure is increased, the equilibrium level of income will also increase by 1 over 1 minus cyd plus cyd times ty and vice versa. The next question is asked to find the partial of c star with respect to g. So we also use the same method, which is to find the partial of c star with respect to g is equal to determination of j2 over determination of j, which is cyd minus cyd times ty over 1 minus cyd plus cyd times ty, which is more than 0. So as a result, the answer we obtain between c star and g is a positive relationship. This means that when the government expenditure is increased, the equilibrium level of consumption also will increase.